All right, guys, so on the screen right now, I have the warm-up question for today, which we need to go ahead and discuss, and then we can get into some notes. We're starting a new unit on forces, and we've already talked about forces some, so some of this stuff is going to be a review because we incorporated some force discussions into the last unit when we did Newton's second law, and then some of it's going to be new stuff like Newton's first law. We haven't actually talked about that one yet. So the warm-up question says to draw a free body diagram for a soccer ball just after it's been kicked rightward at the position shown. So you can see it's off of his foot, it's on its trajectory now. So if you were to draw a free body diagram for the ball at that point, okay, you would need to include the force of gravity, because we know that this object, well, it's on Earth, and it's in free fall. Okay, it's a projectile at this point. It's moving upward. It's going to reach some max height. It's going to come back down. Okay, and so we do know that there is the force of gravity acting on it, and the force of gravity is always a downward force. And so if we were drawing a free body diagram, we would have our box with an arrow pointing down. Would you want to include any other forces? It says no air resistance, so we don't have to worry about that. Okay, do we include the force from his foot when it's at that point? I hear yeses and nos. Is his foot still touching it? No. Don't include it. Okay, yes, his foot had to touch it initially, obviously, in order to kick it. But after it's been kicked, now it's in free fall. Okay, and so we would not include any other forces. We would only include the force of gravity. That's a kind of a misconception that you guys will run into that I've seen before with some students, is that you want to include the force that got it moving, but it's no longer being affected by that force, or it's not applied anymore, so you can't include it in your diagram. Even if it happened before this point, doesn't matter. Okay, if you drew it at this point, it would just be FG down. All right, as I mentioned, we're going to talk today about Newton's first law, which is called the law of inertia, so we're also going to define inertia today. And you have a problem set, 301.1 inertia problem set, which you'll find in My Open Math that you can work on after we go over today's notes. If you're looking for the notes, again, they're also linked in My Open Math. You're welcome to open up the slideshow and follow along if you like. So inertia. Inertia is defined as the resistance an object has to a change in its state of motion. And state of motion is just a more complicated way of saying its velocity. Okay, and so if we're talking about inertia, we're talking about resistance to acceleration, because that would be a resistance to change in state of motion. So if we wanted to come up with a more succinct definition, that would be a good one, resistance to acceleration. So if you're trying to determine how much inertia an object has, or if you want to compare the inertias of two different objects, you can ask yourself a question like this. Which object would be harder for me to accelerate? And we've seen this picture before. Okay, which one of these would be harder to get moving? Yeah, the one that's full of books. Okay, A would be harder to get moving. And that's because it has more inertia. It has more mass. Guys, inertia is directly related to mass. It's a measure of an object's mass by one definition. Okay, and so the more mass an object has, the more inertia that object will have as well. So if you're answering questions about inertia, just think of mass, and if you're comparing two different objects, whichever one has more mass is also going to have more inertia. All right, so Newton's first law, again, is called the law of inertia, and it states an object in motion will remain in motion with a constant velocity, and an object at rest will remain at rest unless acted on by an outside unbalanced force. You've probably heard this before, maybe slightly different wording, but this is Newton's first law. Okay, an object in motion will remain in motion with a constant velocity. An object that's at rest will remain at rest unless there's some force acting on them. Okay, just copy it down. What can you tell me about the motion of this object according to its free body diagram? So I have a free body diagram right here. Okay, and I'm showing you that this free body diagram has two forces acting on it that are equal and opposite to each other. So they're balanced forces. We talked about that last unit. So what could this object be doing? Yes, sir?
At rest or constantly moving.
Perfect. It could be at rest, or it could be moving at a constant speed. I don't know which. All I know is it has 0 acceleration. Okay, I know that object has no acceleration. It could be at rest or it could be at constant velocity. We talked about this in the last unit. And look at what the wording of that says. It says an object in motion will remain in motion with a constant velocity. An object at rest will remain at rest. It's talking about this. When the forces are balanced, that happens. Okay, and that's what it says, unless there's an unbalanced force. Well, we don't have one. We have balanced forces, so that means that this is going to be true. It's either going to remain in motion with a constant velocity, or it's going to remain at rest if it was already at rest. But we have a second one. That one down there, that's the second part of the phrase, unless acted on by an outside unbalanced force, because that one has unbalanced forces. So that object would be accelerating. Specifically, it would be accelerating to the left. That doesn't mean it's moving to the left. It means its acceleration is leftward. Okay, and so we can see that when we have that unbalanced force, and again, that's this part, unless acted on by an outside unbalanced force, that's when we have acceleration. That's when we no longer have objects moving at a constant velocity and objects at rest staying at rest, because now we have something that's going to cause a change in the state of motion. Okay, so again, Newton's first law, law of inertia, it's tying together some of the stuff that we talked about last unit as well, because we've already looked at diagrams just like these. All right, so again, just as a reminder, we've already talked about the terms balanced and unbalanced forces, but obviously when we talk about Newton's first law, we need to know what these mean, because it says unless there's an unbalanced force. So just as a reminder, balanced forces tell us that our system will maintain its constant velocity. That constant velocity, by the way, could be 0. So this could be an object at rest that stays at rest, or it could be an object in motion that maintains a constant velocity. Okay, its acceleration is 0 in either case, and that is because its net force is 0, or the sum of the forces acting on it is 0. So net force or sum of forces, I don't know if you guys have seen this capital sigma in your math class, but it means sum of, so it means adding together all of the forces. But it's net force. It's another way to write it. Unbalanced forces, on the other hand, tell us that the system will experience acceleration. So if those forces aren't equal and opposite, or if they don't cancel out, then you're going to have an object that's either speeding up, slowing down, or changing direction. It will have acceleration. That acceleration isn't 0 because it has a net force that isn't 0. Okay, so it has some non-zero net force, and thus it's going to have acceleration, meaning it's going to change its state of motion. And again, this goes back to what the law said. All right, so again, we've already talked about these terms, so this shouldn't sound new, balanced and unbalanced. We just haven't applied them specifically to Newton's first law, but we've talked about Newton's first law without even realizing it in the last unit, because we've discussed these things already. That's why I said it might feel kind of like a review today. Again, Newton's first law is also called the law of inertia because it describes the tendency of an object to maintain its motion. From this, we know that an object will only experience a change in motion when there's an unbalanced force. That's what the law says. And we can calculate the acceleration it experiences with Newton's second law. So when we have that unbalanced force that causes a change in its state of motion, we can calculate what that change will be using F net equals ma. If we know what the force is and we know the mass of the object, we can determine what its acceleration will be, or if we know any of those two variables, we can find the third. So anytime we have unbalanced forces, that's when we're going to turn and look at this. Now, if we have balanced forces, well, then my net force will be 0, and of course, that would give me 0 for my acceleration as well, if you were solving for it. But again, this just helps to prove Newton's first law, and it ties the two together. As a reminder, net force is the total force or the sum of the forces, and it can be calculated, and must be calculated separately for horizontal and vertical directions. We have not yet dealt with forces that have, or objects that have forces in more than one direction. We've only looked at just horizontal or just vertical, but in this unit, we're going to see examples where we have objects that have forces in maybe 4 different directions, up, down, left, and right, possibly. Okay, so you do need to write this down. When you're calculating the net force, you will have to keep it separate for the horizontal and vertical directions. You will have a horizontal net force, and then you will also have a vertical net force. Now, one of those could be 0. Okay, if there aren't any forces drawn vertically, if it's just horizontally, then yeah, you're going to have 0 for your vertical net force. But you will want to get into the habit of calculating each of them separately so that you can analyze the motion of the object, or the motion that those forces would produce based on that net force. Forces in opposite directions cancel out. Forces in the same direction add together. This is the same thing we talked about last unit, but this is different. If a net force exists in both horizontal and vertical directions, then a resultant net force is drawn at an angle and calculated using Pythagorean theorem or trigonometric functions. We will be using sine, cosine, and tangent in this unit. Okay, we will also be using Pythagorean theorem, a squared plus b squared equals c squared. That one's probably less scary to y'all. I know y'all don't like sine, cosine, and tangent, but we are going to have some trig in this unit. Not today, but I'm just warning you, it is coming, because we will have scenarios where we have forces at an angle. When there's both horizontal and vertical, it's diagonal. Okay, and so we'll have to draw some right triangles and start doing calculations like that. Later, not yet. All right, so I'm going to show you a quick video clip about inertia and car crashes to help illustrate, if it decides to load, to help explain this concept a little bit more with some visuals, and then we'll come back to the notes.
Newton's first law of inertia states that an object stays in motion with the same speed and direction unless acted on by an external force. Normally a car and its occupants move around at the same speed, but when an external force is applied to the car, in this case by the crash test block, the occupants continue to move forward at the same speed until a force is applied to them. This resistance to a change in motion is called inertia, and it applies even when the velocity is 0. It's this property that enables people to do things like this. The china on the table stays pretty much at rest even when the tablecloth's pulled from under it. That's because there's not enough sideways frictional force to overcome the china's inertia and get it to move. Back to the crash test. Because they're not wearing seatbelts, inertia means the occupants of this car continue travelling forwards until the windscreen applies the force to stop them.
Let's look at the inertia here. You can see the vehicle coming forward, it's stopping, but the occupants carry on because there's nothing stopping them carry on. That's the basic Newton's law here. So you can see the occupants, because they're unrestrained, the driver has hit the steering wheel and the whole steering column is crushed around him. You can see he's partially ejected and will be severely injured. The poor passenger, even though he was in the back of the car, protected by the front seat, because he's not restrained, he goes through the front seat and he's gone through the windshield, and you can see his head still sticking out there.
Of course, in real life, you get a lot less time to regret not putting on your seatbelt. Newton's first law gives us the idea that in a car crash, things keep going until something stops them. First used in the 1950s, seatbelts provide an external force that counteracts the passenger's inertia, bringing them to a halt in a more controlled way. But they're just one of the ways car designers reduce the forces on the occupants in the event of a crash. And every car designer also needs to understand the principle behind Newton's second law of motion.
All right. So again, it's the same thing. An object in motion maintains its motion. So if you're in a car and you don't have a seatbelt on and you get in a crash, your car's going to stop because there's an outside force on the car. But unless you've got a seatbelt on, there's no force on you until you hit something. So wear a seatbelt. Buckle up. All right. So inertia is easier to see in the absence of outside forces, but we can't rid ourselves of things like friction or air resistance without being in space or in a vacuum chamber. Even then there's some friction. In orbit around the Earth, astronauts know that once you start to float away, there's no way back unless something or some force opposes that motion. So again, force isn't necessary to maintain motion, but forces like friction can stop motion. So objects in space, especially, an object in motion will continue moving at a constant velocity forever, okay, theoretically, until something acts on it. So that something could be colliding with another object. It could be some other type of external force, if the astronaut throws something. It could be getting too close to the gravitational pull of another planet, okay? So again, unless there's outside forces, things are going to maintain their motion. This is a question that's similar to one that was in last unit. It says, a spaceship in frictionless deep space fires its engines for 3 seconds, which describes its motion at the end of the 3 seconds when the engines are turned off. Okay, so here's the 3 seconds when it fires its engines. So let's say it started at rest. It's applying an external force because the engines are firing, so that external force causes acceleration. So maybe my velocity goes from 0 to 20 to 40 to 60. Okay, but when the engines turn off, now we have no external force anymore. Okay, so we have that net force from the engine causing acceleration at the beginning. My acceleration at the beginning there is 20 meters per second each second. Okay, but when the engine turns off, 0 net force means 0 acceleration. That doesn't mean they're not moving. It means their velocity isn't changing, which means whatever speed they were moving at when the engines turned off, that's how fast they're going. And according to my data table, that's 60 meters per second. So when the engines shut off, they maintain that velocity, 60 meters per second each second, until some other force stops them. That could be the engines again, okay, that change their motion. It could be a collision. It could be something else. But they would keep going at this rate until something stops them. Okay, again, the spaceship will accelerate when it experiences a net force. That's only while the engines are firing. Once the engines shut off, there are no forces at all. Thus, there is no acceleration. The spaceship will continue moving at constant velocity forever, or at least until its engines fire again or it experiences some other force. Again, that's going back to Newton's first law. Again, you don't have to write all that down. That's way too long, but put it in your own words.
So we have to write that?
No. All right, so if you were to draw a free body diagram for each part of this motion, which is what this says to do, then for the first part of it, the red part of my table, I would need to show that I have some force of thrust from the engine, some applied force from the engine, whatever you want to label it as. Okay, but the force from the rocket boosters. Okay, so I have a force there. That's what causes the acceleration. But for the second part of the motion, I can't draw anything here. There are no forces. If you're in deep space, there's no force of gravity. That's the point. You're too far away from another planet. Okay, and there's no air, so there's no air resistance. So there would be no forces to draw unless it's the rocket boosters themselves, the engines themselves. So there's nothing to draw here because you have 0 net force when you're in deep space. How is the spaceship moving when there are no forces acting on it? Well, it was already moving. Okay, again, when the engine shut off, it had a velocity of 60 meters per second, and that's what the first law says. An object in motion, which is this, maintains its motion with constant velocity, okay, until an external unbalanced force acts on it. So it's already moving is the point, and it will keep moving. If it was at rest already, it would stay at rest. Okay, you wouldn't have to keep firing it to keep it at rest either. All right, so again, forces don't keep objects moving. Newton's first law of motion declares that a force is not needed to keep an object in motion. But if you try this, it says let's see it. If you try to push a book or a calculator or something across your desk, it's not going to keep moving. Okay, you're welcome to try. You already know what's going to happen. You push it, it's going to slide to a stop. But that's not because you have to keep pushing things to keep them moving. That's because there's already an external unbalanced force acting on that book or that calculator or whatever it is that you push. There's friction. Okay, so again, the book in motion on the tabletop does not come to a rest position because you stopped pushing it, but rather because there is a force. So it's not because of the absence of one, but because of the presence of friction. Okay, if you were able to remove the friction from your desk, then that book would keep going at the same speed once you released it. And if you had a long enough frictionless surface, it would keep going theoretically forever. okay, because there would be no net force acting on it. All right, so let's go ahead and draw a free body diagram. Again, if you want to add this to your notes, it says draw the free body diagram to illustrate the forces acting on a book after it's pushed to the right and coming to a stop due to friction. So the scenario that we kind of just looked at. Okay, so again, the forces that are present. Okay, we would need the force of friction, it says so. We would also need Fg because we're on Earth, so we have force of gravity. There's a third force that we need to draw as well that we haven't really talked much about. We've mentioned the different types of forces, and I'm going to put them on the screen in a minute. But Fn, that is the normal force. When we talked about it previously, I just mentioned that it existed, and it was a type of contact force, which it is. But normal force is the support force from a surface. So like right now, you're sitting in a chair. There is this normal force between the chair and you that's supporting your weight. And then there's a normal force between the floor and the chair because the floor is supporting the weight of the chair. Okay, so it's just a support force. Your computer right now is experiencing a support force from the desk. But if the object's on a surface, you need to include normal force, which most objects are. Unless you're looking at something that's falling, you're pretty much always going to have normal force. Or if it's hanging, I guess, from a cable or spring, you wouldn't necessarily have it then. Direction of forces. Force of friction would go to the left, and that's because the book is going to the right. Friction is always opposite. We're going to talk more about that in a minute. Fg would be downward because force of gravity on Earth is always down toward the center of the planet. And then normal force is always going to be perpendicular to the surface, which it's a level surface, so directly upward because it's a table. Okay, so again, this is what that free body diagram would look like. I would not include the applied force from the hand because it says after it's pushed. It's just like the warm-up. After it's kicked, I don't include that. Okay, so after it's been pushed, I no longer have to include that applied force. Now it's just sliding on its own. Okay, so this thing is moving to the right, it says so in the question, and yet, look at the free body diagram. It doesn't look like it's moving to the right, but remember, you can't tell which way something's moving by looking at the free body diagram. The net force is to the left. This is moving to the right, it says so in the question. That's why it's slowing down, because the force and thus the acceleration is opposite the direction of motion. It's going to cause it to slow down and eventually stop. All right, here are those forces I was just talking about. Okay, this is slide 15. If you want to go back and write down all these definitions, you can. I'm probably not going to have it on the screen long enough for you to copy them all right now, but you can jot down short versions if you want. But tension force is going to be anytime you have a scenario with a rope or a cable or a string, you're going to want to include tension, which we abbreviate F sub T. Anytime you have an object on a planet, Earth, or a planetary body, it doesn't have to be a planet, the moon. Okay, anytime you have gravity, a gravitational field from a planet or a star or whatever, then you're going to want to include Fg. Most of the time, guys, we're dealing with things on Earth, so Fg is due to Earth's gravitational field, but gravitational force is the force from an object's weight. It always points toward the center of the planet, which is going to be straight down. Applied force is a force from a person who is pushing or pulling an object, or a dog or a machine, whatever. But if you have a scenario where there is a force being applied from an external person, we would call that applied force, and we would say it's F sub A. Normal force, we already mentioned this one, is the force that a surface pushes back with. It's that support force, and it's always perpendicular to the surface, and we abbreviate it F sub N. Frictional force is a force that opposes motion. It's parallel to the surface, and it's the result of the two objects rubbing across one another. There are formulas for some of these, by the way. You'll notice that I have a calculation here for friction. I also had one for gravity. If you want to write down the equations, you can. But frictional force, F sub F, has the equation mu times F normal, or Fn. I put norm here, but it's this one, F sub N. So it's friction is this Greek letter called mu times that. We're going to talk about what that is in a minute. If you want to wait to write down the equation until that slide, you can. But friction force is F sub F. And then the last one is spring force, which is going to be F sub S for spring, and it's the force that restores a spring back to its original shape when it's been stretched or compressed, and we have an equation for that too. Our spring force is equal to K times X. Technically, the absolute value of our spring force is equal to K times the absolute value of X. We're not really going to use that equation probably this unit. We'll see if it shows up in any of our questions. It might. But the other two, FG and FF, we'll see those. But I have them again on other slides so that we can talk about those equations a little bit more.
I have a question, ma'am.
Yes.
First question, so like so do you write all of that down?
You don't have to. It's up to you. They're your notes. This is slide 15. So if you don't have it all down, copy down the slide number and go back and open it up on your own.
Okay, got it.
All right. So we can classify these forces into different types. Contact forces is the first type, and these are going to be forces between objects that are touching. So friction is between objects that are touching. So is tension. You have to pull on the rope. You have to grab it. Normal force, obviously the support from your chair. You're touching the chair. Air resistance, there would be air molecules touching the object as it moves through the air. Applied force and spring force, same thing. All of these types of forces require contact. Can you guys think of any forces that don't require contact, where you don't have to touch for it to happen? I heard gravitational force, and that is a perfect example. There's another one that you probably know, magnetic. Okay, so these are called field forces. Field forces are forces between objects that are not touching, and the two that you're going to be most familiar with are gravitational forces, which is weight, an object's weight, and electromagnetic forces, which would include just magnets as well as electromagnetic fields or electromagnets and all that. Strong force and weak force you may have heard of in your chemistry class, but I honestly don't think they talk about it until AP Chem. So, but it has to do with what holds the atom together. Well, at least strong force does. It's what holds the nucleus together. But we don't talk about those. I'm just mentioning that they exist. Okay, you don't have to know what they are. But these four forces, these four field forces, are referred to as the four fundamental forces. Okay, so if you ever see something that talks about the four fundamental forces of the universe, they are referring to these guys: gravitational force, electromagnetic force, strong force, and weak force. All right. So I told you I have a little bit more about friction, and I'm also going to have a little bit more on FG in a minute. Friction, again, is caused by one surface moving over another. It's a force that can resist the motion of an object. It can prevent an object from moving. If you park on a hill, hopefully there's enough friction to keep your car from moving. Okay, if it's icy, probably not a good idea to park on a hill. I know it doesn't ice much here, but if it did, I wouldn't want to park on a hill because your car might not stay there if there's not enough friction between your tires and the road. Friction can also slow a moving object down. So it can keep you from moving, but it can also slow you down when you're moving. It always opposes the motion or desired motion of the object. Friction depends on the types of surfaces interacting, so how smooth or rough they are, and the normal force between them, so the contact force between them. There are two types of friction: static friction and kinetic friction. Static friction keeps stationary objects at rest. So again, if you park on a hill, you're relying on static friction between your tires and the road, or between your brake pads and your rotors, to keep your car from rolling down that hill. Okay, it keeps you at rest. But once you overcome that, then you have kinetic friction. Kinetic friction slows down moving objects. Okay, so if you have an object that's moving, like you pushed your book across the table a minute ago, then that was kinetic friction bringing it to rest. Frictional force depends on two things. Again, how slippery that surface is or how smooth it is. That is described by mu, that letter that I was in the equation a minute ago. It's a Greek letter. And the normal force. The equation for force of friction is on my screen again. If you didn't get it before, there it is. Force of friction equals mu, which is the coefficient of friction. Mu is, it says always less than 1. It is usually less than 1. We're going to deal with mu values that are less than 1. And if you have Velcro, it's more than 1. But for normal surfaces, it's less than 1. It's basically between 0 and 1. And the higher that number is, the harder or rougher that surface would be, the harder it would be to move the object. If it's frictionless, mu would be 0. Like ice is going to have a very small coefficient of friction because it's pretty slippery. So again, mu is your coefficient of friction, and then Fn is your normal force, which is the support force from the surface that's interacting. So that's the equation.
Quick question, ma'am.
Yeah,
How many questions are in my open map?
I have no idea. All right, so let's go ahead and look at this one. So let's practice drawing some free body diagrams and labeling forces on them. It says draw and label the free body diagram for a duster sitting on a desk. Okay, so if I wanted to draw my free body diagram, I'm going to start with my box. And a good place to start with every free body diagram is with the force that exists on everything that's on Earth, Fg. That's where we're going to start. Okay, Fg we're going to include every time we're drawing a free body diagram for an object on Earth or on any planet. All objects on Earth experience Fg. It is the object's weight. Again, Fg can be calculated as Fg equals mg. That means mass times gravitational acceleration, which on Earth, you already know this number, negative 9.8 meters per second squared. Okay, so if you're trying to figure out how much you weigh in newtons, not in pounds, but in newtons, okay, which is our standard unit, you would take your mass in kilograms and you would multiply it by 9.8, and that would be your weight in newtons. Or the weight of whatever object, this feather duster, for example. Okay, so weight is a force, so it will be using force units. Pounds is also a force unit. It's not the one we use. Okay, we're going to stick with the metric system and SI units. All right, so again, we're going to include Fg. I don't have a number to put on it, so I'm not going to label it with a value because I don't know the weight of this feather duster. If I did, I could include it. So question, if this feather duster is sitting on a desk, should my forces be balanced or unbalanced? Should be balanced, right? Because it's just sitting there. Okay, it's not accelerating, it's not even moving. So I need to include something going up here. And that something needs to be equal and opposite to Fg. That's the normal force. That support force I was talking about a minute ago, that's your normal force, Fn. Okay, so there's my Fn. Objects on a surface will experience normal force. When forces are balanced, Fg will equal Fn. They'll be equal in magnitude. They're opposite in direction, but they will have the same magnitude. Okay, so if Fg was 2, then Fn would be 2 as well. They'd be positive 2 and negative 2, for example. Okay, so again, that's how you can draw a free body diagram from a scenario. Without any numbers, you can still label the types of forces. You just need to start thinking about what forces are acting on an object. And for an object that's sitting at rest on a desk, on the floor, sitting at rest on any surface, your free body diagram will look like this. It doesn't have to be a feather duster. This could be the free body diagram for your calculator. It could also be your free body diagram, your Fg and Fn from the chair. Okay, so again, that is the free body diagram for the feather duster. Here's a follow-up question with my feather duster. It says, a 5.8 Newton duster, okay, they just gave me the weight. And I know that because it doesn't say kilograms, it says newtons. Okay, so a 5.8 Newton duster is pulled rightward across a desk with a force of 5 newtons. If the coefficient of friction between the desk and the duster is 0.41, what is the frictional force? What is the net force? So let's do a practice calculation. Okay, I need to fix my free body diagram though, because now I need to add another force because it's being pulled to the right across the desk, and I need to add friction because it tells me that there is friction. So we're going to redraw it like this, and I'm going to put numbers on it. If you want to label all these, you can. This is still Fn. This is still Fg. This is Fa. It's applied force because it's being pulled. And then we have Ff. I don't know what Ff is. That's part of the calculation here. All right, so again, if you're doing a calculation and you're dealing with forces like this where you have multiple forces, draw a free body diagram every single time. And then we're going to label everything too. Okay, so if I want to label my givens, I know Fg is negative 5.8. I know I didn't label it with a negative, but the arrow's already pointing down, so I didn't have to write the negative when I drew it on the picture, but I do want to write the negative when I label it. Okay, I have Fn, that's positive 5.8 newtons. I have Fa as positive 5 newtons because it's to the right. Right is positive, up is positive. Down and left are both going to be negative. And then I have mu from the question, 0.41. That is not the same as Ff. We have to use it to find Ff in just a moment. In fact, that's what we're going to do right now. So the first thing the question asked for is what is the frictional force? So frictional force, we have an equation for it, mu times Fn, and look at that, I have mu, I have Fn. Okay, you'll notice that they did not tell me Fn in the question, but just like the previous feather duster that wasn't accelerating vertically, this one's not either, it's only going to the right. So I knew that it was balanced vertically, and therefore I know that Fn is equal to and opposite to Fg. All right, so from here we can plug in 0.41 times 5.8, that is mu times Fn, and that gives me a frictional force of it doesn't give you the negative sign, you have to add it. It gives you 2.378 newtons, but in your mind you need to look at that picture and say, but it's pointing to the left. It's not going to give you the negative, you have to add it on. When it's pointing to the left, add on a negative. Okay, so negative 2.378 newtons. That's the first part of the question. The second part says, what is the net force? Well, I don't have a vertical net force. Vertically, it's going to be 0. So all I really want to look at is my net force horizontally, F net x. We're going to use x for horizontal. We're going to use y for vertical. I did not bother writing out F net y because F net y is 0. But F net x is not 0 because my applied force is 5 and my friction is only 2.378. Again, net force is the sum of your forces, but forces are vectors. So if it's pointing to the left, include the negative sign. You're really subtracting here, not adding. 5 plus negative 2.378, or 5 minus 2.378, is positive 2.622 newtons, and that would be the net force acting on my duster. Questions about this? We're just adding a tiny calculation in here with force of friction. Otherwise, it's all the same stuff from last unit. All right, free body diagrams. We've seen these before. Which of these could have 0 momentum? A, B, C, or D. You can pick more than one if you want, or none. Do any of them have 0 momentum, or could they have 0 momentum? What does 0 momentum mean? Let's start there. It means what does my velocity have to be for my momentum to be 0? 0. I have to be at rest. So I'm asking which of these could be at rest. And at rest means balanced forces. So which ones have balanced forces? C. Anything else? A. A and C could have 0 momentum. They don't necessarily have 0 momentum. They could be moving. I don't know. If they are moving, they would have constant velocity, which means the answer to my next question is still A and C. Because if they were moving, those two would have constant velocity. They could be at rest or they could be moving with constant velocity. Okay, what direction is object A moving? Do you guys know? Me neither. We don't know. That's the point. It could be moving up, down, left, right. It could be at rest. We have no idea. All we know is that it's not accelerating. Any of these could be moving to the left. Any of these could be moving to the right. Any of these could be moving up. Any of them could be moving down. Only 2 of them could be sitting at rest, A and C. The other 2 would have to be accelerating. Okay, so they wouldn't be sitting at rest, but they could be moving in any direction. All right. Let's tie it together with graphs. Which of the following could show the motion of the object depicted in the free body diagram? I just said this could be moving any direction. So let's look at each of these graphs and describe the motion shown by the graph and figure out if that makes sense for that free body diagram. So for this XT graph, this object is moving backwards and it is slowing down. I know that because it has a negative slope, and I know that it slows down because the slope gets horizontal. So could that free body diagram be moving left and slowing down? If it's moving left, is it slowing down? Let me ask you that.
Yes.
Yes. If it's moving left, it would be slowing down. So that could be true. Okay, if it's moving left, it would be slowing down because the net force is to the right, which means the force is opposite its motion. All right, for the next one, this graph shows an object moving to the right and speeding up. It starts at rest and it's getting faster and faster and faster in the forward direction. Could that be true for that free body diagram? Yeah. If it's moving to the right, guess what? It's speeding up because its force is in the same direction, which means its acceleration is in the same direction as its velocity. It's going to get faster. So that could be true. What about the last one? That one is showing rightward acceleration. Yep. Okay, that is also possible for this free body diagram. Okay, that doesn't mean everything is possible for every free body diagram, but yes, any of these could show the motion of this object. We don't know which way the object's moving, so they could be possible solutions. What about these? Do they match? Again, if you're not sure, describe each one. A shows an object moving forward at a constant velocity. Could that be true for this free body diagram? No. That free body diagram is not constant velocity. B shows an object that's moving to the right and slowing down. Could that be true? No. Because if this object was moving to the right, it would be speeding up. So no, these free body diagrams can't match, that free body diagram does not match those graphs. Okay, it doesn't show constant motion like A, and if it were moving to the right, it would speed up, unlike B, so it doesn't match that one either. Guys, what would make that? How could we get a graph like this? What would our free body diagram need to look like? Anybody know? Balanced forces. Any free body diagram with balanced forces. Could be that one, that one, that one. Anything with balanced forces could produce that graph. Could. Not necessarily does, but could. That could be true. All right, that's it for today's notes. So you guys don't have a ton of time. You've got like 9 minutes. So if you make your way to My Open Math, you're looking for 301.1. So go ahead and get that opened up. It should be a pretty quick one. But if you don't finish it in class, then it is homework. It is due by 11:59 p.m. But it should be pretty quick because it doesn't really have math in it. So go ahead and get to work. If you have any questions as you're working, please let me know.